Hello everyone, this is Monica Lupion and this presentation is the second part of the lecture 12, Steady State Molecular Diffusion. In previous presentation, I covered the study of mass transfer without chemical reaction, and we saw three different cases. One is the unimolecular diffusion or the diffusion through a stagnant layer. Then the pseudo steady state diffusion, or the case where there was a boundary condition moving with time. And third, the equimolar counter diffusion, which I mentioned that it's really important in many cases of mass transfer. Those were cases without chemical reaction. But how would be the approach to these problems if there is chemical reaction involved? We're gonna make a distinction between two different cases. One is the case of homogeneous reaction. You have a diagram here. So in general, there is a reaction happening all over the control volume. So it has a direct impact in the mass transfer. The second case is the heterogeneous reaction. And when there is only the reaction happening not homogeneously within the control volume, but like in this case, over the catalytic surface. So it happens in a very located position within the mass transfer problem. And we'll see that although this heterogeneous reaction, of course, also has an impact in the mass transfer, but the formulation will be different. We're going to consider this heterogeneous reaction more like a boundary condition and not, we will include the influence of the reaction in the general formulation. In general, as chemical reaction occurs, both the diffusion and the reaction rate are important, and we distinguish two different cases. When the reaction rate is fast, we say that the process is controlled by diffusion. That will be the bottleneck of the problem. And on the contrary, if the rate of diffusion is fast, in that case, the bottleneck will be the chemical reaction, and we say that it's the process controlled by the reaction. Examples of the two cases that we're going to cover, the heterogeneous cases and the homogeneous cases. Most of the cases, when we can consider heterogeneous reaction, the general equation is simplified because, as I mentioned, we don't consider the influence of the chemical reaction in the general equation, but more like a boundary condition. So if there is a case of heterogeneous reaction, we can consider that this term here, A, is equal to 0. And one good example of this heterogeneous reaction is when the reactions are happening over the surface of a catalyst. Second case, homogeneous reaction. We need to consider this term RA, and it is related to the kinetics of the process. Depending on the grade of the process, the order of the chemical reaction, we may have different equations here. In this case, in this example, is the first order chemical reaction. So this RA parameter is equal to the minus the chemical reaction rate constant times the concentration. So depending on the order and depending on the different concentrations of the species involved, we will have different equations here expressing the rate of the chemical reaction. Let's begin with the easiest case when we have heterogeneous reaction. There is an example very good in your textbook in the chapter 26, which is about a catalyst particle, and there is a description of the different steps that you need to follow. I will solve that example in a separate presentation. When the chemical reaction is not heterogeneous but homogeneous, the problem could be more complex because we can simplify this parameter RA, but we need to take this parameter into consideration. If we do the same analysis than in previous cases, that is, we consider a steady state and one dimension, the equation 1 is simplified. And if we also consider that the system is dilute, that if you remember from a few minutes ago or the previous presentation, I explained that when the system is dilute, we can consider that the bulk contribution in the Fick rate equation is very small, and therefore the Fick rate equation only has the contribution of the diffusivity. So combining 1 and 2, the general equation 1 and the Fick rate equation 2, if we combine these two, this is the general equation in the case of having homogeneous reaction. In this particular example, we are considering that the chemical reaction is first order, and it's only influenced by the concentration of A. But again, depending on the conditions of the kinetics of the chemical reaction, this term here will be different. This equation here is describing the case of one-dimension steady state process with homogeneous reaction. If you want to solve it and apply the boundary conditions, is something, it looks like this. So as you can see here from the solution, the problem gets more and more complicated. As I mentioned in previous classes, this course is not related to your skills for the mathematical resolution of differential equations. So for the exams and the quizzes, I won't ask you to solve this complex differential equation because I also assume that you have the tools and the skills necessary to solve those, or you can solve those equations using, for instance, MATLAB. This is the case of one dimension, but what happens if we have a more complex geometry and we have 2 and 3 dimension systems? As you can imagine, the problem gets more and more complicated as we increase the number of dimensions. 2 and 3 dimension systems are in general much more complex to solve than 1 dimension systems. The methodology here will be exactly the same. We can get if we get the first equation of the general equation and we apply steady state conditions and no chemical reaction, and on the other hand we have the Fick rate equation and we apply the same concepts, then these are the two equations that we need to combine and solve, applying the boundary conditions expressed here in this diagram, and this will be the solution of the equations, where this parameter here, an, are the Fourier coefficients. Okay, let's move to the study of the simultaneous momentum, heat, and mass transfer. There are different examples. Many physical situations involve the simultaneous transfer of mass, energy, and momentum. An example is, for instance, when you paint a surface is drying, so there is volatilization of the solvent, and at the same time, if you're using some kind of forced convection, some fan or some heating system to accelerate the drying process, there will be also energy and momentum transfer. As you can imagine, when it comes to the simultaneous transfer of mass, energy, and momentum, the solution of the problem gets more complicated. But we're gonna cover a few ideas in lecture 14 and 15. Today, I just wanted to highlight a few examples. For instance, a simultaneous transfer of heat and mass when there is a condensation of vapor upon a cold surface, or when the momentum and there is a simultaneous transfer of momentum and mass transfer, for instance, in an absorption column. This is an example of a simultaneous transfer of heat and mass, and it's a very common unit or equipment in industry. It's called the cooling towers, and here you have a picture of a power plant and probably a nuclear plant where you need to cool down the refrigeration water. And in order to cool down the temperature of the water, you normally have this kind of like a paraboil chimney where you can use air and the difference in the concentration, that is the humidity, to cool down the temperature of the water. Normally what you do with a cooling tower is comprised by some spray nozzles that will spray the hot water that we are trying to cool down, and because of the evaporation of water, there will be an energy transfer there, and as a consequence, the temperature of the cooling tower will get down, and also the temperature of the water. As I mentioned, this is a very typical equipment used in industry for many years. In this diagram is just a power plant where I assume you know more or less how it works. A quick summary is you have a boiler where you burn fuel, for instance, natural gas or coal or biomass, and because of the heat that is being produced here inside of the boiler due to combustion, steam is generated, and this steam goes to a turbine where power is produced. But then you need to cool down the flue gases coming from the boiler because of environmental regulation, and also because you need to clean up this flue gas before emitting to the atmosphere, and some of the equipment that you use to clean up this flue gas, they are not able to operate at a very low temperature. So for those reasons, you need to cool down the air or the flue gas, and you use water to cool down, and then water needs to be cooled down as well. So that's why you use this cooling tower that I just described in previous slide. In the case of this particular case, the simultaneous transfer of mass and energy has been widely studied and analyzed, and now it's relatively easy. This psychometric diagram is just a graphical representation of the different equations that you will have to solve, but luckily for us, the utilization of this diagram is much more easier than just solving all the equations. I'm pretty sure you're familiar with this diagram. There are different entries and there are different parameters that you can calculate. But as I mentioned, this is just a graphical representation of the different equations that you will have to solve when it comes to the simultaneous transfer of energy and mass. Okay, right. So I would like you to try this example. As I mentioned, mass transfer, it's in general more complicated than heat transfer, so don't get discouraged, and just make sure that you understand all the different steps, and if you have any question at all, it's better if you raise the issue now, because later when we continue with the lectures and continue with the classes, it will get more and more complex. So it's better if you take some time now to study the basics and to understand the basics before moving on.